still got carbon and silicon. Hey, where are those coming from? See, here they've just got these two components. Well, we'll find out. I guess you'll have to wait just a minute because I want to show you something first. We took one of these red chips, we took several actually and did this, 4 of them. We presented data in the paper. Here's one, and it produces, as you look at it, a red chip produces this, let's see, this is, what am I doing here? Make sure, this is after it was separated out with MEK. So it's not this particular chip, it's a chip that we separated out with MEK. I want you to look particularly, I'm focusing here on the iron-rich region. So as we soak this in this paint solvent, we've got regions of iron oxide, see the oxygen peak there, it's enormous. Iron oxide, and then other regions of aluminum-rich and silicon-rich in different regions. By the way, separating the aluminum from the silicon like that means this is not an aluminosilicate. Paint solvent does not reduce aluminum. Okay, it doesn't make aluminum out of aluminum oxide or out of aluminosilicates. Somebody says you're looking at kaolinite. I say, you get serious. We just use a paint solvent. We can't get aluminum out. You know, how do you separate the silicon from the aluminum, for one thing, in aluminosilicate with a paint solvent? No. Get serious. Okay. But he couldn't publish that, obviously. I'm waiting for someone to go ahead and publish a response to our paper. I welcome it. But they better be serious science or it's not going to pass peer review. The peer review on this paper, by the way, was rigorous. It took months. One of the things we did, encouraged by the peer reviewer, he had about half a dozen pages of comments on our paper. He was actually complimentary, but at the same time he said, look, you got to check this, you got to check that, this and that. And so we did. It took months of further experiments. One of the things we did is to look for spheres produced. These happen to be iron-rich spheres when they're metallic and shiny that we found in abundance after we heated this red material to ignition. So we got it to go off. I'll show you some more data on this, how this stuff ignites. But the point is, we see spheres rich in iron. Look at oxygen down now. Iron's much more than the oxygen. It turned out, if you quantify this, it's not an exact feature, but again, it's Jeff, look at the quantification. We have more iron than oxygen after the reaction. This implies than before. So here we've got iron oxide, lots of oxygen. Now the iron has been reduced, we say in chemistry. The oxygen has been taken up by something, presumably the aluminum. And so what we have then, this is a very important test, iron, not all of it's oxidized after the reaction. And furthermore, you have spheres that form. There were no spheres of this size. These are 1 micron or larger that you can see here. This 50 micron bar. No spheres 1 micron or larger before the reaction. We did this several times. And yet a lot of these iron-rich spheres after. Folks, we nailed this. This stuff is a thermitic reaction. It's a thermitic material. And we know the temperature which reacts. I'm getting there. But let me show you some. This is another sphere from the red chip ignition. We see often aluminum and silicon and iron in these spheres. Sometimes we see some that are very rich in iron. Just want to emphasize, this is in the paper. You also see spheres that have aluminum and silicon as well. As you'd expect from the thermitic reactions, you've got aluminum and silicon in this red material. Sometimes the spheres capture some of that aluminum. Notice the aluminum now is reduced. In the red chips, it's almost always that the aluminum and silicon are close to equal. I'm not quite sure why. It's how they were fabricated. But after reaction, the aluminum is reduced. We're presuming that the aluminum oxide, a lot of it goes off in this effluent. This now is from, these are spheres found in the World Trade Center dust. Written another paper on that, and it's in a Journal of Metal and Studies. It's evidence for extremely high temperatures. That paper, I don't remember the full title, but you can Google on high temperatures. Journal of Metal and Studies, you'll find it. Okay. Anyway, we find a lot of these spheres in the dust that are rich in iron. And look at, we find a lot of them have iron and aluminum and silicon. Folks, that's a very unusual combination in molten metal in the dust from the World Trade Center. Where else did it come from than from a reaction, as we have here, from the ignition of these red chips? But again, that's not central to the argument. It's important, but what's central to the argument is these red chips are thermitic. I'm trying to give you some more of the data that can be followed up on. Commercial thermite is in the paper as well, both of these. Here's again the spheres from the dust. This is from commercial thermite. John Perula's here. Again, this is the coarse thermite, but it had silicon in it. I was rather surprised that that's the way it came from the manufacturer. And you see in the spheres from commercial thermite, which he collected, John collected this residue. And then we looked at the spheres. We see these spheres are very much like what we see in the World Trade Center dust. This is known thermite. This is spheres from the World Trade Center dust. How do you get so many spheres in the dust that have iron and aluminum and silicon if it's not from thermite? Okay? That's additional information pointing to the use of thermite. Let's look at this just for a minute. This is the molten metal. A friend of mine stabilized the image. This is an amateur photographer. This is the South Tower just minutes before its demise. Oh, did you see the dust going off there? The white dust going off in this orange-white material, which can be compared to the thermitic reaction, which I ran. I know this is thermite, and the white ash flowing off from that. Let me say that there could be two types of, at least two, the very fine, ultrafine thermite that we see in the Redbird chips, as well as ordinary conventional thermite. That's quite possible in the towers. Okay. Pause just for a minute when you read that. Drink of water, the report. We're going to talk now about nanothermite. Also called superthermite from published literature. It's in the public domain. A lot of this research is done by the defense laboratories, for the Department of Defense and so on. This is in the public literature. I'm not telling any secrets here. It's out there. You can read it. We quote it in our paper. You can go to the references and read all about nanothermite. Some of you will want to do that, like Jim. Okay. This is from 2000, April publication. That means they've been working on this for some time before that. And of course, it's before 9/11/2001. Over a year. Energetic nanocomposites of iron oxide and metallic aluminum, they discuss in the paper. The compositions are stable, safe, and can be readily ignited. Aha. I still want to know about silicon and carbon. Where are those coming? We'll find out. Here we go. Energetic nanocomposites are a class of material that have both a fuel, aluminum, and oxidizer, iron oxide, for example. There are other oxidizers possible. Intimately mixed, and where at least one of the component phases meets the size definition. And typically, as I see in the literature, that is about 120 nanometers. One of the components has to be less than that. Turns out that the grains of iron oxide are already less than that, about 100 nanometers. Jeff will pinpoint that in the TDM. I hope that gets published. He's a little worried about being. Anyway, that's another story. Someone will do the TDM, we'll get that nailed, the exact diameter. And of course the aluminum in these plates, very curious plates that are about 40 nanometers thick. Here is an EDS map